Awesome. Hello, everyone, and welcome to Content Security Policy, a successful mess between hardening and mitigation. We're super happy to be here today. This is Mickey. My name is Lucas. We're both from Google Switzerland. And yeah, Hawaii is awesome. Really enjoying this conference. So it was really worth the travel. OK, we have a pretty stuffed agenda today. We have some general recommendations that should be usable for developers and security experts, but we also have some pretty advanced topics where we go very much into detail. So if there's questions, feel free to ask them at the end, or we're around at the conference, so we're happy to chat about CSP 24/7, just to grab us. Yes, so Mickey will start with vulnerability trends, and I'll take over in a bit.
Awesome.
This is forward.
This is the forward, okay, great. Okay, hi everyone. So we'd like to start with real-world data. So we focus on cross-site scripting or XSS vulnerabilities, right? And this is also what we aim for when we mean CSP. CSP is this like huge umbrella security header, which was originally thought as like solving many of web security issues. But we focus on XSS in all our previous talks and in these talks too. So we wanted to start with real-world data, and what we have is like all the XSS vulnerabilities reported to us, to Google, in the vulnerability reward program since 2014. And you can see that like around 2/3 of them are actually web application, web platform bugs. And drilling down in these web platform bugs, we see that approximately 3/4 are cross-site scripting XSS vulnerabilities. So XSS is a major problem, and this is reflected also outside of Google in other sources of data, other bug bounties or vulnerability reward programs. So for example, HackerOne has similar results, and also Mozilla. In Mozilla, bugs reported to Mozilla, we see that XSS is actually the top vulnerability reported there. So there is need of defense in depth in this field, mostly because the web platform is not secure by default. Unfortunately, we are still not there. So it is important, especially for very sensitive web applications, to have some kind of defense in depth mechanism in case the primary security mechanism, which should not be neglected at all, and actually people should focus on them in case they fail. And we'd like to spend a word on what we call mitigations, because mitigation is a very complex and overloaded word. It actually comes mostly, the first mitigations in computer security are in the, let's say, memory safety world. So mostly for mitigating exploitation of buffer overflows and so on, right? And when we talk about web mitigation techniques, these are a little bit more recent, more modern. So we believe there are, not mitigations are made equal, and there are some good mitigations and some mitigations that are less good, and I'd like to start with them first. So some mitigations aim to just raise the bar. So they have an economy, and their mindset is based on an economy of cost. They want to make costly for an attacker to exploit a vulnerability. They want to slow down the attacker. So in this case, in the web world, I would say that a traditional CSP, which you might have seen or read in our previous papers and talks, the whitelist-based CSPs are automatically bypassable. Also, as Jim said earlier on, more than 95% they're automatically bypassable. So an attacker has just to find a bypass in the whitelist to exploit the same bug. Right, the same bug that was there. So in this way, the mitigation technique did not really reduce the attack surface. But on the other hand, good mitigation techniques are the ones that also reduce the attack surface by, for example, disabling unsafe APIs. So for example, not having unsafe eval, we'll see later the details in a CSP policy, means that all eval-based XSS cannot happen. So this is an actual reduction of the attack surface. And this is what we call a good mitigation. There are other examples like for nonce-based CSP, but we'll see later in great details. Another important thing is good mitigations should actually induce hardening, what we call hardening of the application from a code point of view. For example, CSP, a good CSP actually induces the developer to, for example, refactor inline event handlers, which are bad for security, or to use contextual auto-escaping templating systems, which greatly increases the security with respect to reflected XSS. So with this, I go through a little bit more in detail, like which kind of XSS were blocked at Google by CSP. So this is real-world data. It's the first time we present with this detail. Coverage of CSP at Google. So this effort has been mostly 3 years, and in 3 years we are covering 62% of all outgoing Google traffic with an enforcing nonce-based CSP. These are more than 80 Google domains. So Google has a lot of domains, subdomains, as you might guess, but 80 is still a pretty significant number, and more than 160 services. And for very sensitive domains, the traffic coverage with what we call strict CSP is very close to 100%, and the number of services that have almost total coverage of strict CSP is around 70%. How many XSSs that were reported to us got blocked by CSP? So in 2018, more than 60% of XSSs that got reported to us got mitigated successfully by our CSP. Among 11 XSS vulnerabilities on very sensitive domains, 7 of them, which is around 78%, got successfully prevented by CSP. And taking into account all the 69 XSS vulnerabilities on sensitive domains, we have around 60%. So here in numbers with pie charts, on the left, very sensitive domains, on the right, all the sensitive domains. And going a little bit more in detail, on the very sensitive domains, 11 XSSs got reported. Of them, 9 were happening on endpoints that were covered by CSP, and CSP coverage is actually a problem. Maybe we'll go into that a little bit later, because it's important to cover all of your endpoints with CSP. And of these 9, 7 were mitigated by CSP, and the other 2 that were injection in the SRC attribute of script could have been mitigated by what we call an additional whitelist policy. So we'll see later, this is a pretty advanced thing. We're not going full circle and advocating for whitelist-based policies, so please bear with us and we'll show you exactly what we mean. And of the 2 that were not covered by CSP, the XSS could have been mitigated by CSP. We see here a detail of our XSSs that got reported in 2018. We see here the causes, the root causes, what they were being exploited via, and there are many sinks or injection points. But what I'd like to highlight is that JavaScript URI plus inline event handlers plus data URI make up for approximately 1/3 of the injection points. And so having a CSP that just didn't contain the unsafe inline keyword that actually covers these sinks, as shown in this table, would be enough to actually mitigate successfully for 1/3 of the vulnerabilities. This was also slightly surprising for us. It's pretty cool confirmation. So in this table, we have XSS sinks on the left, and what makes CSP successfully block them. So there is not really a one-on-one mapping of this, to be completely honest, but this is good enough to give an idea. So for example, for JavaScript URI, it's just not having a safe inline. It's enough to block them. The same for data, and the same for inline event handlers. So then we have inner HTML context that can be either inner or not inner HTML context, which means either a reflected XSS that gets reflected by a server, or a programmatic injection in the inner HTML property of a DOM element. And both are prevented by not having unsafe inline in the policy. Then we have eval, which is governed by the unsafe eval directive, keyword. And then we have injections in the text of a script tag, which also here can be both programmatic and reflected. CSP helps if we hash the script, or if we nonce and manually nonce it. So strict dynamics makes adoption easier, but also makes trust propagation. And we'll see later what it means. So not having strict dynamic and manually noncing is the way to protect against injection in the text of the script. And it's very likely the same for the SRC attribute of the script. Then we have some kind of complex web frameworks that do some symbolic execution, or they try to parse, and they have their own templating languages, but will not go into that now. And here I pass to Lucas for some more detail.
Yes, thank you so much, Mickey. In this section, we would like to introduce some common CSP recipes that you, as developers or security engineers, can reuse. They basically are ordered by the ease of deployment and by the amount of sinks they're covering. Everything we talk about in this section is about nonce-based CSP, and I will give a very quick intro about that as well. And it's a kind of a mix of like high-level stuff, like just use this policy and you will get these guarantees, versus like a really detailed explanation of like what kind of guarantees you will get for that, right? So that you not just like blindly trust the CSP, because people say, yes, they have a CSP, but what does it mean, right? They could just allow everything, or they can also have a default source none policy that blocks everything, right? It really doesn't tell you anything. So the obligatory slide on why not the whitelist, I feel like almost like a broken record on Twitter, telling people to not use whitelist anymore. Thank you. So the thing is, usually they're trivially bypassable because, as Jim already mentioned, we did a study a couple years ago based on the Google search index. We took all the CSP policies we found. Almost all of them were whitelist based. And as soon as you know a couple of JSONP endpoints or AngularJS libraries hosted on popular CDNs, you basically can bypass all of them, right? And even if you only allow self, as soon as you have like a JSONP endpoint or you host some AngularJS library, it also makes your policy completely bypassable. So basically, with a whitelist, you tie the security to the policy not being bypassable per se, rather than actually closing a sink. And there's a couple of talks we had in the past, so there's links in the bottom. You can look them up later. We'll not cover this topic into any more detail today. What we will cover is nonce-based CSP. And I just wanted to ask the audience, have you heard about nonce-based CSP before, or is it the first time? Awesome, some hands up. Nice. So just a quick recap. The idea is basically only scripts that have a random nonce attribute that is random per response will be allowed to execute. And this nonce value in the script tag has to match the nonce value in the response header, the content security policy response header. Only then the browser will execute this script tag. So in that case, if you have a markup injection and the attacker injects a script with an invalid nonce or without a nonce, the browser will block this script from executing. So CSP is a client-side defense and depth strategy, right? So nonce-based CSP has been around since many years. It was actually introduced in CSP2, but it was not really picked up by anyone. The reason is that this is very hard to deploy in normal applications. So in CSP3, strict dynamic got added. It's a small modification. It basically instructs the browser to also allow scripts to execute that are created dynamically within an already trusted script. So this makes a huge difference because the only thing you have to do now is actually nonce scripts in the response body, and you don't have to nonce all the scripts in your application. And that's especially important if you, for example, load widgets from third-party sites where you don't control the JavaScript, right? If they do like a dynamic script creation, you will not be able to make them pass the nonce. Or you can file a feature request and hope that they do it, but usually that's a blocker otherwise. So what we'll focus in this part is basically incremental rollout of content security policy. Rolling out CSP is often a trade-off between the amount of sinks, XSS sinks you're actually covering with your policy, and the effort to roll out the policy, which is mostly the refactoring work you have to do. If you remove a sink, right, like if you remove an unsafe API like evil, you have to make sure that the application is not using this sink, right, otherwise it will break. So there is a refactoring effort. And the refactoring is mostly based on the type of CSP, like how many sinks you're closing, and your application, of course, like the size of your application, the amount of inline event handlers, the code quality, etc. So we came up with a couple of templates that basically we mapped on the following slides to the table that Mickey presented you before. So if you start at the bottom, you basically have a lot of remaining attack surface, but it's very easy to adopt. If you go further up, it's harder to adopt, but you cover more sinks. And the goal is eventually to get up to a nonce-only policy, I guess. But it is not possible in every application, right? And since it's locomoco-sec, we also have a level 1 CSP that uses like brand new CSP free features that haven't been presented anywhere else yet, I think. It's very interesting for some use cases, but usually I would recommend to start either with a level 2, level 3 CSP, and if you can, move up to a nonce-only CSP. So, level 2 CSP is like an arbitrary definition we choose for a nonce-based CSP that has strict dynamic and also unsafe eval. It's kind of a sweet spot because it's kind of easy to roll out because the refactoring effort is kind of manageable, but it covers a lot of very common XSS sinks. As a matter of fact, this type of policy is set on 60% of all the outgoing Google traffic on sensitive domains, and that was the one that Mickey meant with which mitigated between 60 and 80% of the XSS. So it's a good starting point, but if you can, you should go further. The nice thing is, because it's a nonce-based policy, it mitigates all the classical reflected and stored XSS in your application, right? And it also works if you don't control all the JavaScript yourself. If you have a widget that you load from Facebook, Twitter, Google Analytics, whatever, and these widgets dynamically create script tags, they would still work with this type of policy. And there is good browser support, which is also nice. The drawbacks of this type of policy is you still haven't covered the eval sync. And since they're strict dynamic, a portion of the DOM XSS is still uncovered. So here's the list of the sinks that are covered. JavaScript URIs are covered because this policy does not have unsafe inline. It might have unsafe inline, but this is just for browser backward compatibility. Every browser that supports nonces will drop unsafe inline implicitly in the presence of a nonce. Also, data URIs are covered because there's no unsafe inline. The HTML injection into HTML context and inner HTML context is also covered because every script tag needs to have a nonce to be executed. Eval is not covered because you have unsafe eval in that policy. And then there's a very interesting section which is injection into script text and script src. So if you have code that does like create element script .src and then assigns some user-controlled input or script.innerText assigning to user-controlled input, that's not really covered because strict dynamically propagates trust to these child scripts. Inline scripts would be covered if you replace this with a hash. Yes, and also AngularJS like template injections are not covered because these happen entirely in JavaScript, and CSP basically has no access to that. So in this case, we really recommend just to move away from AngularJS because it's kind of broken, and you should use like Angular 2 and up because they have a offline template compilation, which doesn't have these kind of bugs. So that's very interesting. What kind of refactorings you have to do to make your application compatible to this type of level 2 CSP? First, you have to remove JavaScript URIs. Second, you have to refactor inline event handlers. Usually you remove them and instead use the JavaScript API to register event handlers. It's usually not a lot of work, but if you have a lot of inline event handlers, it can sum up, right? And the other thing you have to do is you have to basically nonce all the script tags that are in the response body, not the dynamically created ones. This just works because of strict dynamic, and that basically is a huge advantage in terms of refactoring. So One step further, level 3 CSP is nonce-based plus strict dynamic, no unsafe eval. Exactly the same properties, just that you basically now have only the DOM XSS sinks that are going through the script text, script inner text, and script SRC. Eval is covered by this policy. So also almost the same refactoring steps. You just, in case you have eval, you have to refactor it to something else. Like if you use it for JSON parsing, you can use the native browser APIs, JSON.parse. If you do module loading, you can like create child scripts. And there's also a very interesting variant of this type of policy, which is actually hash-based and not nonce-based. This policy is extremely useful for static or single-page applications, which are static, and you don't want to have a nonce on a static page, because nonces should not be cached, and if you have a nonce on a static page, it's not static anymore, right? So what you can do is you can replace the nonce with a hash of a kind of a bootloader script, and you do the same refactoring steps as before, but you basically move all these source scripts into the bootloader script and just like dynamically load them. By that, script dynamic will make sure that these kind of things are allowed, and only that one script will be allowed to execute in the initial markup, because that is the hashed one. And if you know the CSP evaluator, it actually uses this kind of policy because it's also a static site. You can check out the page code and look at it as an example. And then there is kind of the holy grail for nonce-based CSP, which is a nonce-only policy. Why? Because it actually really covers the vast majority of XSS sinks that are tractable for CSP. It's supported by all major browsers, even Safari, and it's very nice property, has very nice properties because it basically means every script is running was explicitly marked as trusted by a developer with a nonce value, right? So on the other hand, the drawback is that you now have to nonce all the scripts, which means you need to have some nonce propagation mechanisms to dynamically created scripts, right? So what you now have to do is, skipping ahead one slide, I'll show you that in a second. What you now have to do is, you also have to do like a set attribute nonce on dynamically created scripts. Looks easy, might be easy in your application, but if you use a lot of external widgets or you do like very complex stuff, this can become a lot of work and maybe even impossible if you don't control all the JavaScript code. In terms of the covered XSS sinks, this policy performs really well. The only injections that are left are like, if the developer marks something as trusted with the nonce, and then they still put like a user input into a script tag, in the script SRC, then that's still exploitable, right? But there's no automatic propagation of nonces in this model. And also very important to note here, you must not add a whitelist here now, right? Because then it's an or thing, either a nonce or a whitelist. That would make the policy bypassable. Yes, so here's a nice overview about all these properties. And there's also a column for trusted types, which is a talk held by Koto in the afternoon, Christoph Kotovic. And it's really awesome because it is very well performing on all the DOM XSS parts. And it complements CSP perfectly, right? Trusted types is a JS-based hardening, and it doesn't apply for stored or reflected XSS, server-side. For that, you would need to have CSP as a mitigation. But for the client-side code, it's really awesome. So really recommend going to that talk as well. Yeah, CSP coverage at Google, we already mentioned that to some extent. The only thing I want to highlight here is we basically, all our services that are covered by CSP started with a level 2 CSP. And then last summer, we started to slowly upgrading to level 4 CSPs with eval. And just this year, we also started to upgrade the policies to remove evals. So almost 10% of the outgoing traffic has a level 4 policy now for Google. And we mostly do this for super sensitive services, but even the just level 2 CSP was quite effective in mitigating quite a lot of XSS externally reported XSS attacks for Google. Here's an example of, like a very short example of domains that already have it. For example, photos.google.com has a level 4 CSP. It's a very complicated application. It's totally doable. It just takes a bit of time and dedication. And yes, we prioritized by domain tiers. So very sensitive domains got the most attention, and they almost 100%, like I think 96% covered by a level 2 CSP, and the level 4 CSPs, they're on already 4%. So with that, we move to advanced CSP techniques. Some of that is really advanced, but it's also quite novel, and we thought like Locomoco is probably the audience to present that, right? So new in CSP3, there is 2 new directives, which is script source element and script source attribute. Same thing for styles, but we'll talk about that later. The difference is it's like script source, but these two basically cover different parts of what the script source directive would cover. Script source element just covers script tags, right? Inline scripts and source scripts. And script source attribute covers all the script execution that happens through attributes in HTML tags, right? Like inline event handlers or JavaScript UIs. Why is this useful? Because through this thing, you now can use hashes of attributes, like hashed inline event handlers or hashed JavaScript UIs, and explicitly bless a couple of inline event handlers. So if you have a site where you, for some reason, cannot refactor some inline event handlers, with this type of policy, you would still be able to roll out CSP without breaking your site. It's not the thing I would shoot for first, but it's definitely an interesting development. It's, as I said, it's brand new and it's only supported in Chrome 75. That's also a limitation. Other browsers will probably follow, but it will take a bit of time. The big benefit of that policy is that there's like almost no refactoring required. And of course, having this policy is strictly better than having no CSP, right? Because the classical reflected XSS, server-side XSS are still covered by this policy. Drawback is, of course, that this policy covers not all the things that good nonce-based CSP could cover, right? And in case of an HTML injection, there's also a culprit here, because if you hash inline event handlers, in an injection, an attacker could reuse these event handlers as long as they are hashed. So if you have an inline event handler that is like delete user, and then there's a markup injection, and someone injects like image tag x, source x on error, delete user, that would execute, right? If you just whitelist return false or JavaScript weight 0, that is not really relevant, but this is very important to mention here. And yeah, the attacker doesn't have full script execution in that case, but it's still a thing, right? I can't go into detail because of time reasons, but here's a small POC that you can try out yourself if you want to learn more about it. The covered sinks are similar to the level 2 CSP, but now here the inline event handlers also have like a tilde, because depending on what you hash, you have a different security guarantees. The nice thing about this policy, although, is that you can actually use this for static content and auto-generate a policy. So if you have static content, you could have a proxy that hashes inline event handlers and puts nonces and generate a CSP for that on the fly. That's the first time that this is possible. But it should be static content, right? And not something that has templates or user controllable input or whatever. Refactoring is really easy. It's just basically adding nonces to scripts in the response body and hashing these things. So yes, that's a new thing in CSP3. And then there is also something else that is pretty useful sometimes, which is double policies or multiple CSP policies. I don't know if you're aware of it, but you can actually send more than one CSP header in a single response. Why would you do this? Because it basically allows you to really add even more constraints to what the policy allows. Usually, if you have only one script source directive and you put nonce random and self in the same directive, it's an or operation, right? A script will execute if any of these requirements are fulfilled. If you set these as two separate policies, they will be enforced independently by the browser, and the script, in order to execute, has to pass both policies. And you can either set double or multiple policies by having separate headers, separate content security policy headers, or you have a single content security policy header and separate them with a comma. This looks basically like that. If you comma separate them, it's very important to not confuse that with the semicolon, right? But this is a HTTP header specification. Multiple value headers are separated by commas. So what does this thing do? There's two CSPs. One is a whitelist, and the other one is a nonce-based CSP. And the script will only execute if it fulfills both properties, or if it fulfills the properties of both policies. In that case, this script executes because it has the random nonce. And in that case, and it also executes because the script is sourced from the same domain. In the second and the third example, the script does not execute because here's the nonce is missing, and here it's not the same domain source. So if you would basically merge these into here, into single policy, all of these would execute, right? So this is really the nice thing about this type of policy. And we use this in a couple of places at Google. It has the nice feature that actually also nonce scripts that get redirected would be covered by this policy. And also injection into script SRC are much more limited to what they can do. The drawback is, of course, now you have to have a nonce-based policy and you need to maintain a whitelist, right? Which is actually quite complex. So not the first thing I would shoot for, but for high sensitivity applications, definitely worth looking into. And it also reflects here, right? It's actually pretty strong. And yes, so almost done with the guru section. Last bit is what about style injections? Like if you have a markup injection, you don't only can inject script tags, of course, right? You can also inject style tags. And because of CSS3, there's some pretty advanced attacks you can carry out. They are using CSS selectors or import statements. The very important thing to mention here is that these only work in style blocks or sourced styles, and they don't work in inline styles. So what you can do is you can use style source, nonce, and a random token to basically enforce a nonce on all the style tags. That is the preferred solution, of course. But since inline styles are so frequently used, it's a refactoring nightmare, right? So you can use the new CSP3 directive for styles and basically enforce the nonces just for the style blocks while allowing arbitrary inline styles, right? This is a mitigation strategy, right? But you definitely block the more powerful CSS selectors and import statements. And of course, this policy can be combined with script source policies. And with that, I'll head over to Mickey for the productionizing CSP part, and we're almost done.
Awesome. So now we talk about what you'd actually deploy CSP in your website. You'd like to see what's going on. So what is being blocked, and if there are more refactoring steps needed, or if there are even some attacks and you want to be aware of them. So normally you can put a report URI, and a so-called CSP violation report is sent by the browser every time a resource is blocked to your collection endpoint, and then you can store them in a database and then look at them. It is very helpful in this case to add the report sample keyword. This instructs the browser to add a sample of the blocked JavaScript, actually the first 40 bytes, in the script sample property. And this is really, really cool because you can actually distinguish between actual things that need to be refactored from, for example, extension noise, which are false positives. Here I want to be really quick about CSP fallbacks. So CSP has been designed across many years, and the browser's support of CSP is a little fragmented, so it's important to have backward compatible CSP policies that actually falls open on older browsers. So you can take a look at that later, but very simply, I'll just say two rules. Unsafe inline is ignored in presence of a nonce or a hash, and any whitelist is ignored in presence of strict dynamic. Everything else is more advanced. So for example, the strict dynamic policy that we presented earlier with the nonce and strict dynamic, which should be just nonce and strict dynamic for CSP3 compatible browsers like modern Chrome, Chromium, Firefox, Opera, and so on. Actually, sometimes it's presented with HTTPS, which is a broad whitelist, and unsafe inline. So why? This is very confusing, right? But this makes it so that the same policy actually works across all browsers. So browsers that do not understand strict dynamic actually see HTTPS because strict dynamic makes the whitelist disappear, and browsers that do not understand anything just have a fail open policy, which is with the unsafe inline. Of course, it doesn't provide any security guarantee, but it does not break your site. Sorry about that. So this is very overwhelming, right? So CSP is a mess, right? It is a mess for us too, and we worked on it for more than 3 years. It has a lot of complexity, like so many directives, so many gotchas, like there is this and there is that. This makes this no longer work, and I saw you enjoyed the comma a lot. It's really hard. But what I'd like to make very clear is that you don't need to know all of this. You don't need to go through all the levels and variants of CSP that we presented. But to have a reasonable amount of security for your web application, you can actually get it pretty simply. And what we suggest is to start with a strict dynamic policy. And a level 2 policy is a good trade-off between security and ease of adoption. If possible, upgrade to nonce only. This makes it even better. But actually, as we said already, 60 to 80% of XSSs at Google in 2018 were already blocked by a strict dynamic-based XSS. And the usual reminder, CSP is a defense in depth mechanism, so you should fix the bugs. You should not just put slap. Yes, we say it every time. Like you should not just slap a policy on it, right? It's very important. It's very important. It's not an excuse not to fix the underlying bugs, right? And please take also verify your policy with the CSP evaluator tool, which focuses on XSS protection. So, very briefly, wrapping up. Please use a nonce-based CSP policies with strict dynamic if you care about XSS protections. Sorry, that was level 3, it was not level 2. If you can without unsafe eval, depends. And if possible, upgrade to nonce only, so which is our level 4. Also maybe add the fallbacks, which makes it harder to read. And mahalo, thank you very much.
Thank you so much, everyone.
If you have any questions, please.
Oh, cool. Awesome. So can you describe the amount of time, energy, and process that went into refactoring the JavaScript code at Google in order to broadly support CSP? Well, yes, it took a long time. Can we have the questions also on the screen, maybe? Okay, no worries. So it depends. So for the strict dynamic-based content security policy, the refactoring was mostly focused on removing inline event handlers and less so on refactoring JavaScript. For upgrading to a nonce-only policy, it almost took us like, I think 12 or 18 months to basically refactor all the libraries at Google to do nonce passing and basically teach the frameworks to do it, right? Now we're at the spot where we basically just have a framework that has a nonce-only policy and does auto-noncing on a context-sensitive templating system. And the module loaders, they propagate the nonces, they use safe types internally. And basically, when you create a new application on that framework, the developer doesn't even need to know that there is a CSP, right? It just works out of the box. But it was quite some journey there, but I think it was worth the effort. And with the CSP coverage going up, we also saw bugs being mitigated. So.
Cool. So the other question is, have you had any successful XSS attempt against an L4 policy? So,
absolutely.
Yes. The L4 policy is a nonce-only policy, right? Without anything else. Yes, we do, of course. So I would say there are maybe two main kinds. Like one is when you have an injection in the script src, so in the source attribute of a script that is actually nonced or blindly nonced. And another is when actually you can upload user content on the same origin. So for example, if you can upload some JavaScript or SVG or some HTML and you can actually embed this, this might be a problem. Or of course you can instruct the victim to go there directly. But this is a little bit out of scope because it's actually a coverage problem, it becomes coverage problems, and the blindly noncing is one.
Yes, so the user upload is actually mostly a problem for non-Chrome, because Chrome, if you have a nonce-only policy, also blocks the PDFs and this kind of stuff. But I think
yes, together also with the object src, and there are also the plugins, and so XSS is really, really complex, right? It's very hard to say we can cover 100%, and this is also not the aim of a mitigation technique, right? But we can cover a lot, and we can cover a lot in a pretty effective way.
So I think the TLDR for level 4 policies, if the developer nonces a script and still puts something untrusted user controllable input in the src, it's still bypassable, right?
WebAssm.
Which one is it? This one. WebAssm, yes. It appears that nonce-based policies work for execution of WebAssm. Is that correct? If so, I am now very happy. I think for WebAssm, you have to have unsafe eval to allow it to execute. I think they were discussing about an unsafe WASM directive, but I think it's not part of the specification yet.
More directives.
So, yes. So it is possible, but you have to put unsafe eval. Do your bug bounty researchers still report XSS bugs even if they can't bypass CSP? Yes, they do, and yes, they should, because they're still getting paid. And if they also bypass the CSP, I think they get paid extra. So please don't stop reporting bugs.